Picture this: you're standing on Earth, looking up at the night sky, and somewhere out there, 4.2 light-years away, is our nearest stellar neighbor, Proxima Centauri. 4.2 light-years. That's 25 trillion miles. To put that in perspective, if you could drive there at highway speeds, 60 miles per hour, non-stop, no bathroom breaks, it would take you 45 million years. The journey would span the entire evolution from early hominids to modern humans more than 10 times over. But we're not talking about driving. We're talking about flying. We're talking about the most audacious journey humanity has ever contemplated. A journey that makes Columbus crossing the Atlantic look like a stroll to the corner store. Because flying to Proxima Centauri isn't just about distance. It's about confronting every law of physics that governs our universe, every limitation of human engineering, and every assumption we've made about what's possible. Let's start with what we know. Proxima Centauri is a red dwarf star, the smallest and coolest of the 3 stars in the Alpha Centauri system. It's barely 1/7 the diameter of our Sun, and if you could somehow stand on its surface, you'd weigh about twice what you weigh on Earth. This star is ancient, probably around 4.85 billion years old, roughly the same age as our solar system. And orbiting this dim, red ember is at least one potentially habitable planet, Proxima Centauri b, discovered in 2016. Proxima b sits in what we call the habitable zone, that Goldilocks region where temperatures might allow liquid water to exist on the surface. It's about 1.3 times the mass of Earth, and it completes an orbit around its star every 11.2 days. Think about that. A year on Proxima b is shorter than 2 weeks on Earth. But here's the catch: because Proxima Centauri is so cool, the habitable zone is incredibly close to the star. Proxima b orbits at just 5% of the distance between Earth and the Sun. That means this planet is likely tidally locked, with one side perpetually facing the star, baked in eternal day, while the other side freezes in endless night. Is there life there? We don't know. Could there be? Maybe. Is it worth the journey to find out? That's the question that haunts every astronomer, every physicist, every dreamer who looks up at the night sky and wonders what's out there. Now, let's talk about getting there. Our fastest spacecraft to date is the Parker Solar Probe, which reached speeds of up to 430,000 miles per hour as it dove toward the Sun. That's fast. That's really fast. That's 0.064% the speed of light. At that velocity, it would still take you 6,500 years to reach Proxima Centauri. That's longer than all of recorded human history. The pyramids would be built, rise, and fall into ruin multiple times over during your journey. So clearly, we need to go faster. Much faster. And this is where things get interesting, because the physics of going fast, really fast, approaching even a fraction of light speed, becomes absolutely wild. First, let's consider what it would take to accelerate a spacecraft to, say, 10% the speed of light. That's 18,600 miles per second. At that speed, you could travel from New York to Los Angeles in less than 0.2 of a second. The entire circumference of Earth would flash by in under 1.5 seconds. You'd reach Proxima Centauri in about 43 years. A human lifetime. Suddenly, the journey becomes theoretically possible within a single generation. But here's the problem: acceleration. Newton's second law tells us that force equals mass times acceleration. To accelerate even a small spacecraft, let's say 1 ton, to 10% light speed in a reasonable time frame, say 1 year, you need continuous thrust equivalent to about 3,000 times the power output of the entire International Space Station. And we're talking about a 1-ton spacecraft. Not a ship capable of carrying humans, life support, food, water, and all the equipment needed for a multi-decade journey. Scale that up to something livable, maybe 100 tons, and you're looking at energy requirements that dwarf anything humanity has ever produced. Let's put some numbers on this. The total energy required to accelerate 1 kilogram of mass to 10% the speed of light is roughly 4.5 times 10 to the 14th joules. That's 450 trillion joules. For a 1-ton spacecraft, multiply that by 1,000. Now multiply by another 100 for a realistic crewed vessel. We're talking about 45 quadrillion joules of energy. The entire annual energy consumption of the United States is about 94 exajoules, or 94 quintillion joules. So you need about 0.5% of America's total annual energy output just to get your ship up to speed. And that's not counting the energy needed to slow down when you arrive. Oh, you thought you'd just fly by? No. If you want to actually explore Proxima Centauri, study the planet, maybe even orbit it, you need to decelerate. Which means you need just as much energy to slow down as you used to speed up. Double your energy budget. So where does this energy come from? Chemical rockets are out of the question. The best chemical rocket fuel, liquid hydrogen and liquid oxygen, releases about 13 megajoules per kilogram. To accelerate our 100-ton spacecraft using chemical propulsion, you need more fuel than exists in all the oceans on Earth. Literally. The mass ratio becomes absurd. You'd need a fuel tank the size of a small moon. Nuclear fission? Better, but not by much. Fission reactions release about 80 million megajoules per kilogram of uranium-235. That's a huge improvement over chemical rockets. But you're still looking at needing hundreds of tons of nuclear fuel, plus the massive reactor to control the reaction, plus the radiation shielding to protect your crew. Your spacecraft starts to resemble a flying nuclear power plant. Nuclear fusion offers even more promise. Fusion reactions, like those that power the sun, can theoretically release about 300 million megajoules per kilogram of fuel. Now we're getting somewhere. With fusion, you might be able to build a spacecraft with a reasonable mass ratio. Projects like the Daedalus study in the 1970s explored exactly this concept. A two-stage fusion rocket that could theoretically reach 12% the speed of light using pellets of deuterium and helium-3 as fuel. But here's the thing about fusion, we haven't mastered it yet. Not really. We can create fusion reactions in laboratories and experimental reactors, but we haven't yet achieved net positive energy output in a controlled, sustained way. Every fusion reactor built so far has required more energy to run than it produces. The ITER project in France, the world's largest fusion experiment, hopes to achieve net positive fusion by the late 2020s or early 2030s. And that's just proving the concept. Building a compact, lightweight fusion engine capable of powering a starship? That's decades beyond that, at minimum. Let's say we crack fusion. Let's say we build the engine. Now we face another problem: fuel storage. Deuterium is relatively abundant, but helium-3? That's rare on Earth. Really rare. The best place to get helium-3 is the Moon, where solar wind has been depositing it in the lunar regolith for billions of years. But even there, concentrations are measured in parts per billion. You'd need to strip mine enormous sections of the lunar surface to gather enough helium-3 for a single interstellar mission. We're talking about establishing a massive industrial infrastructure on the Moon before we can even think about launching toward Proxima Centauri. And we haven't even talked about the real killer, interstellar space itself. Space isn't empty. We like to think of it as a vacuum, and compared to Earth's atmosphere, it is. But between stars, there's still stuff. Hydrogen atoms, mostly, but also dust grains, stray molecules, cosmic rays. On average, there's about 1 hydrogen atom per cubic centimeter in the interstellar medium. That doesn't sound like much. 1 atom per cubic centimeter. But when you're traveling at 10% the speed of light, even individual atoms become deadly projectiles. Imagine this: a single hydrogen atom, essentially just a proton and an electron, sitting peacefully in space. Now imagine hitting it at 18,600 miles per second. At that speed, the collision releases energy equivalent to a particle accelerator beam. Each atom impacts your spacecraft with kinetic energy of about 7,000 electron volts. That single, tiny atom hits with the force of a bullet relative to its size. Now multiply that by the trillions of atoms you'll encounter every second of your journey. Your spacecraft gets sandblasted by what amounts to a continuous particle beam weapon. This is called erosion, and it's a serious problem. Any exposed surface of your spacecraft will gradually wear away under this constant bombardment. Paint vaporizes. Metal oxidizes and ablates. Even the toughest materials we know will degrade over decades of exposure. You need shielding. Lots of it. But shielding adds mass, which increases your energy requirements, which makes everything harder. Then there are the bigger pieces. Dust grains. These are larger than single atoms, typically a few micrometers across, but rare in interstellar space. About 1 per cubic kilometer. Again, doesn't sound like much. But over the course of a 40-year journey covering 4.2 light-years, you're traversing about 40 trillion cubic kilometers of space. That's 40 trillion chances to hit a dust grain. When you hit one at relativistic speeds, it doesn't just scratch your paint. It explodes. A grain of dust the size of a speck of pepper, striking at 10% light speed, releases energy equivalent to several sticks of dynamite. It punches straight through any conventional hull material like it's tissue paper. The solution? More shielding. Maybe a sacrificial outer layer that can absorb impacts. Maybe a magnetic field to deflect charged particles. Maybe a cloud of plasma pushed ahead of your ship to vaporize incoming debris. All of these ideas have been proposed. None are simple. All add mass and complexity. And we haven't even mentioned cosmic rays. These are high-energy particles, mostly protons, accelerated to nearly light speed by supernova explosions and other violent cosmic events. They zip through space with energies millions of times higher than anything we can produce in our most powerful particle accelerators. When they strike matter, they don't just cause erosion. They trigger nuclear reactions. They create showers of secondary particles. They damage electronics. They mutate DNA. On Earth, we're protected from cosmic rays by our atmosphere and magnetic field. In space, astronauts on the International Space Station experience radiation levels about 10 times higher than on Earth's surface. But the ISS orbits within Earth's magnetosphere, which still offers some protection. In deep space, beyond the Sun's heliosphere, the cosmic ray flux is even higher. And it's constant. Unrelenting. Over the course of a 40-year journey to Proxima Centauri, astronauts would accumulate radiation doses that would almost certainly cause cancer. Probably multiple cancers. The solution, again, is shielding. Water works well because hydrogen atoms are good at absorbing radiation. So you surround your crew compartment with water tanks. But water is heavy. You need meters of water thickness to provide adequate protection, and water masses 1 ton per cubic meter. The shielding alone for a small crew compartment could mass dozens of tons. Add that to your 100-ton spacecraft, and now you're looking at accelerating 200 tons to 10% light speed. Your energy requirements just doubled. Let's pause here and consider what we've assembled. A massive fusion reactor, tons of rare helium-3 fuel, meters-thick radiation shielding, armor to protect against dust impacts, life support systems to keep a crew alive for 4 decades, plus all the scientific instruments and equipment needed to study Proxima Centauri when you arrive. You're not building a spacecraft anymore. You're building a small city. A flying city that needs to reach speeds that make our fastest jets look like they're standing still. Oh, and did I mention you need to pack food and water for 4 decades? Even with the most advanced recycling systems, you'll need reserves, backups, redundancies. A human needs about 2 kilograms of food and water per day. Over 40 years, that's about 30 tons per person. For a crew of, say, 10 people, you're looking at 300 tons of consumables. Unless you can grow food on board. Which means you need hydroponics bays, artificial lighting, seeds, soil, or growing medium. More mass. More complexity. The spacecraft we're describing is starting to look less like Apollo and more like the Death Star. Minus the planet-destroying laser, plus fusion engines. And we haven't solved the fundamental problem. Where does all this mass come from? Where do you build it? How do you assemble it? How do you launch it? You can't build this on Earth. The gravity well is too deep. To escape Earth's gravity, you need to reach escape velocity, about 7 miles per second. Every kilogram of mass you want to launch from Earth's surface requires enormous energy just to reach orbit, let alone interstellar space. No, if you're building an interstellar spacecraft, you build it in space. Maybe in Earth orbit. maybe at a Lagrange point, maybe on the Moon, where gravity is 1/6 that of Earth. But building in space presents its own challenges. There's no air, obviously, so no conventional construction equipment. Everything needs to be done with robots, or astronauts in spacesuits, or remotely from Earth with long signal delays. Every bolt, every weld, every component needs to be transported to the construction site. You need to establish a supply chain stretching from Earth to space. You need infrastructure, orbital factories, fuel depots, repair facilities. You're not just building a spacecraft. You're building the entire industrial capability to support interstellar missions. The cost? Astronomical. Literally and figuratively. NASA's entire annual budget is about $25 billion. The Apollo program, adjusted for inflation, cost about $250 billion over its decade-long run. Building an interstellar spacecraft? We're talking trillions. Multiple trillions. The kind of money that makes national budgets look like pocket change. This isn't a project for one nation. This is a project for all of humanity. A multi-generational, international effort that would require cooperation on a scale we've never achieved. But let's say we do it. Let's say humanity comes together, pooling resources, technology, and talent. We crack fusion. We establish lunar mining operations for helium-3. We build orbital construction facilities. We design and test the systems needed to keep humans alive for 4 decades in deep space. After 50 years of development, 100 years, we're ready. We launch. The ship accelerates away from Earth, its fusion engines burning with the light of a small sun. Week by week, month by month, it picks up speed. After a year of continuous acceleration, it reaches its cruising velocity, 10% the speed of light. The engines shut down. The ship coasts through the darkness, a tiny spark of human ambition crossing the vast emptiness between stars. On board, life settles into routine. The crew, carefully selected and trained for this mission, maintains the systems, conducts experiments, exercises to prevent muscle atrophy in the low-gravity environment. They watch Earth shrink to a pale blue dot, then vanish entirely among the stars. They're alone now, more alone than any humans have ever been. If something goes wrong, if a critical system fails, there's no rescue. No mission control can help. The radio signals from home take months, then years to arrive. They're on their own. The ship is their entire world. A small bubble of Earth, of humanity, hurtling through the cosmic void. They live in recycled air, drink recycled water, eat food grown under artificial lights. They age. Children born on the journey, if the mission planners decide to include families, will grow up never having seen Earth except as a point of light. They'll be the first humans born between the stars, citizens of no planet. And slowly, gradually, Proxima Centauri grows brighter ahead. After 20 years, it's noticeably brighter than the other stars. After 30 years, it's the brightest object in their sky besides the distant sun. After 40 years, it's a blazing red beacon, growing larger by the day. Now comes the hardest part, deceleration. The ship needs to slow down, or it'll just fly past Proxima Centauri at 18,600 miles per second, getting a few hours of observations before shooting off into the depths of space beyond. But slowing down requires just as much energy as speeding up. The fusion engines, carefully maintained for 4 decades, fire again. The ship shudders with the force of its own thrust, gradually bleeding off velocity. This takes years. Years of continuous braking. The crew, now middle-aged or elderly, waits. Finally, the ship slips into orbit around Proxima Centauri. The mission planners have timed everything perfectly. They're positioned to study Proxima b as it makes its 11-day orbit around the star. Telescopes and sensors, dormant for most of the journey to save power, come online. For the first time, human eyes, human instruments, see an alien world up close. What do they find? That's the billion-dollar question. The trillion-dollar question. Maybe Proxima b is a barren rock sterilized by stellar flares from its temperamental red dwarf star. Proxima Centauri is known for violent outbursts, eruptions of X-rays and ultraviolet radiation that would strip away any atmosphere and scour the surface of any life. Maybe the planet's magnetic field, if it has one, protects it. Maybe there are sheltered valleys or underground caves where liquid water persists and life clings to existence. Maybe there are oceans on the day side, kept from boiling away by a thick atmosphere that redistributes heat. Maybe there are storms, continent-sized hurricanes driven by the temperature difference between the eternal day and eternal night hemispheres. Or maybe, just maybe, there's life. Not intelligent life necessarily. We're not talking about aliens with cities and radio telescopes. But maybe simple life. Microbial life. Organisms that thrive in the cracks and crevices of this hostile world. Finding even a single microbe on Proxima b would be the most profound discovery in human history. It would mean we're not alone. It would mean life arises wherever conditions permit. It would mean the universe is probably teeming with life, on countless worlds around countless stars. But what if there's nothing? What if Proxima b is dead? What if the journey, the decades of flight, the trillions of dollars, the collective effort of humanity, all lead to a lifeless rock? Is it still worth it? I'd argue yes. Because the journey itself is the point. The act of reaching out, of testing our limits, of proving we can cross the interstellar void. That's what defines us as a species. That's what separates us from every other organism on Earth. We're the ones who look up and ask, "What's out there?" And then we build rockets to find out. Now let's talk about alternatives. Because fusion rockets, while theoretically possible, are brutally difficult in practice. Are there other ways to fly to Proxima Centauri? Other propulsion systems that might be easier, cheaper, or faster? One option: light sails. Imagine a spacecraft with no engine at all. Instead, it unfurls a massive, ultra-thin reflective sail, kilometers across. A powerful laser, positioned in orbit around Earth or the Sun, fires a beam of light at the sail. Photons have no mass, but they carry momentum, and when they bounce off the reflective surface, they push. It's a tiny push per photon, but with a powerful enough laser and a light enough spacecraft, you can accelerate to impressive speeds. This is the concept behind Breakthrough Starshot, a project announced in 2016 by physicists Stephen Hawking and billionaire Yuri Milner. The idea is to build thousands of tiny spacecraft, each massing just a few grams, equipped with light sails and miniaturized electronics. A ground-based laser array, powered by gigawatts of energy, would fire at these tiny probes, accelerating them to 20% the speed of light in a matter of minutes. At that speed, they'd reach Proxima Centauri in about 20 years. The beauty of this approach is that you don't need to carry fuel. The energy comes from the laser, which stays behind in the solar system. Your spacecraft can be incredibly light, which makes acceleration much easier. And because you're not planning to slow down, just fly by and take pictures, you only need energy for the initial push. The challenges? They're considerable. Building a laser powerful enough to accelerate even a gram-scale spacecraft to relativistic speeds requires technological advances we haven't achieved yet. We're talking about a laser array covering several square kilometers, capable of firing with perfect precision at a target that's rapidly receding into space. Miss by even a fraction of a degree, and your beam flies off into empty space, completely missing the sail. And the sail itself needs to be incredibly reflective, incredibly light, and able to withstand the intense heat from absorbing even a tiny fraction of the laser's energy. Then there's the question of what you do when you arrive. A gram-scale spacecraft can carry a camera, a radio transmitter, and basic electronics. That's about it. No scientific instruments. No landing capability. No ability to orbit and conduct detailed studies. You get one pass, lasting a few hours at most, during which you need to collect all your data, take all your pictures, and transmit them back to Earth. And that transmission, traveling at light speed, will take 4.2 years to arrive. So the total mission time from launch to receiving data is about 24 years. Fast by interstellar standards, but still a generation. Another option, antimatter. matter and antimatter annihilate when they meet, converting their entire mass into energy according to Einstein's famous equation, E=mc². This is the most energy-dense reaction possible in the universe. 1 kilogram of antimatter, annihilating with 1 kilogram of matter, releases about 90 quadrillion joules of energy. That's about 4,000 times more energy than the same mass of fusion fuel. With antimatter, you could theoretically build a spacecraft that reaches a significant fraction of light speed with a reasonable fuel load. NASA's Institute for Advanced Concepts has studied antimatter propulsion systems and concluded that a few milligrams of antimatter, combined with clever magnetic nozzle designs to direct the energy, could accelerate a small probe to relativistic speeds. The problem with antimatter is simple: we can't make it in useful quantities. Particle accelerators like the Large Hadron Collider produce antimatter, but only tiny amounts, a few atoms at a time. The current world production of antimatter is measured in nanograms per year. To fuel an interstellar mission, you need grams, maybe kilograms. At our current production rate, it would take billions of years to produce enough. And that's not even considering storage. Antimatter annihilates instantly when it touches normal matter, so you need to contain it in magnetic traps, isolated from the walls of its container. This requires energy. Constant energy. If your containment fails, even for a microsecond, your fuel explodes with the force of a nuclear bomb. What about generation ships? If we can't make the journey in a single human lifetime, what if we embrace the timescale? Build a ship large enough to support hundreds or thousands of people. A ship with farms, forests, rivers. A fully self-contained ecosystem that can sustain human civilization for centuries. Launch it toward Proxima Centauri at a more modest speed, say 1% light speed. The journey takes 400 years. The people who launch won't see the destination. Neither will their children, or their grandchildren, or their great-grandchildren. But eventually, after countless generations born and died in the metal corridors of the ship, their descendants arrive. Generation ships are the stuff of science fiction, featured in novels and movies for decades. The concept is appealing because it doesn't require impossible physics. You don't need fusion or antimatter or light sails. Just a really big ship and a really long time. But the challenges are more biological and social than technological. Can humans survive for 400 years in a closed environment? Psychologically, I mean. We're adapted to Earth's environment, with its seasons, its weather, its vast landscapes. What happens to people who live their entire lives inside a spaceship? Who never see the sky, never feel rain, never stand on ground that isn't metal? Studies of isolated communities, from Antarctic research stations to submarines, show that humans can adapt to confined spaces for months or even years. But generations? That's untested. Then there's genetics. A population needs genetic diversity to remain healthy over many generations. Inbreeding, even mild inbreeding, leads to accumulation of harmful genetic mutations and increased disease susceptibility. You need a founding population of at least a few hundred people, carefully selected for genetic diversity, to maintain a healthy gene pool over 400 years. And you need social systems to encourage genetic mixing, to prevent the formation of isolated subgroups that might become inbred over time. And what about culture? The people who arrive at Proxima Centauri won't remember Earth. It'll be a legend to them, a myth told by their ancestors. Will they even care about completing the mission? What if they decide, after 200 years in flight, that they'd rather turn back? Or settle on an asteroid somewhere along the way? Or just keep flying forever, making the ship itself their permanent home? You can't control what people 400 years in the future will choose. You can only hope that the mission remains important to them. Let's consider another approach entirely. Don't send humans. Send robots. Or more precisely, send AI. Artificial intelligence doesn't need life support. It doesn't need food or water. It doesn't age, at least not in the biological sense. An AI probe could operate for decades, centuries even, without the constraints that limit human missions. This is basically what we do with all our deep space probes today. Voyager 1 and 2, launched in 1977, are still operating after more than 40 years, currently traversing interstellar space at about 38,000 miles per hour. They'll never reach another star, they're not aimed at any, but they prove that we can build machines that function for decades in the harshness of space. An AI probe to Proxima Centauri could be small, light, and equipped with sophisticated sensors and experiments. It could study the star system in detail, even deploy smaller subprobes to orbit planets or land on surfaces. And when it gathers data, it transmits it back to Earth. Yes, the transmission takes 4.2 years, but we're patient. We've waited billions of years for life to evolve to the point where we can ask these questions. We can wait a few more decades for answers. The counterargument is that robots, even sophisticated AI, can't replace human judgment. A robot can follow its programming, but what if it encounters something unexpected? Something its creators never anticipated? A human scientist can adapt, improvise, ask new questions in response to surprising results. A robot can only execute its pre-programmed instructions, at least with current technology. But AI is advancing rapidly. Machine learning systems can now recognize patterns, make decisions, even exhibit creativity in certain domains. Perhaps by the time we're ready to launch an interstellar mission, we'll have AI sophisticated enough to truly explore autonomously, to make discoveries we never imagined, to act as humanity's eyes and minds across the light years. There's another concept that sounds like pure science fiction but is grounded in real physics: the Alcubierre drive. Proposed by physicist Miguel Alcubierre in 1994, this is a theoretical method of faster-than-light travel that doesn't actually violate relativity. Instead of moving the spacecraft through space, you move space itself. The drive creates a bubble of curved spacetime around the ship. Space contracts in front of the ship and expands behind it, carrying the ship along like a surfer on a wave. Inside the bubble, the ship isn't moving at all, so it doesn't experience relativistic effects or require enormous energy for acceleration. With an Alcubierre drive, you could theoretically travel to Proxima Centauri in days or weeks, not decades. You could explore the galaxy, visit hundreds of stars, and return to Earth while your friends and family are still alive. It's the ultimate solution to interstellar travel. Except it probably doesn't work. Or at least, we don't know how to make it work. The Alcubierre metric, the mathematical description of how such a drive would warp spacetime, requires something called negative energy or exotic matter. This is matter with negative mass, which pushes instead of pulls. We've never observed negative mass in nature. It may not exist. Quantum field theory hints that negative energy densities might be possible in certain circumstances, like the Casimir effect, but only in tiny amounts and only under very specific conditions. Scaling that up to wrap a spaceship in a bubble of negative energy? No one knows if that's even theoretically possible, let alone practically achievable. And even if you could build an Alcubierre drive, there are other problems. When you turn it off, when you stop and return to normal spacetime, calculations suggest you'd release a blast of high-energy particles and radiation that would sterilize everything in front of the ship, including your destination. You'd arrive at Proxima Centauri only to discover you've accidentally fried the very planet you came to study. Not ideal. So warp drives, while tantalizing, remain firmly in the realm of speculation. Maybe someday we'll discover new physics that makes them possible. Maybe we'll find a way to generate and manipulate exotic matter. Maybe future generations will look back and laugh at our primitive understanding, the way we look back at medieval scholars debating how many angels can dance on the head of a pin. But for now, with our current understanding of physics, faster-than-light travel appears impossible. Which brings us back to the slow, hard way, accelerating through normal space at sublight speeds, crossing the light years through sheer persistence and engineering. Let's talk about the human element more. Because even if we solve all the technical challenges, even if we build the perfect spacecraft with unlimited energy and flawless systems, we still need to address the question of who goes and why. Volunteering for an interstellar mission is not like signing up for a trip to Mars. Mars is 8 months away. If things go wrong, rescue might be possible. Communication with Earth is delayed by minutes, not years. You can return home. An interstellar mission? That's one way. Even with the fastest propulsion systems we can imagine, the journey takes decades. You will spend the majority of your remaining life on that ship. You will likely die before reaching the destination. And you will never see Earth again. Never walk on grass, never feel wind, never see another human outside your tiny crew. What kind of person volunteers for that? What motivates someone to leave behind everything and everyone they know for a destination they'll never reach? Is it scientific curiosity? A sense of adventure? A desire to be part of something greater than themselves? Or is it something darker, a desire to escape, to run away from Earth and its problems? History gives us some guidance. Throughout human history, people have undertaken perilous journeys to unknown lands. The Polynesians crossed the Pacific in canoes, navigating by stars to find islands they'd never seen. European explorers sailed into unmapped oceans, not knowing if they'd find land or fall off the edge of the world as some believed. American pioneers crossed the continent in covered wagons, leaving behind the comfort and safety of established towns for the uncertainty of the frontier. And today, there's no shortage of people who'd volunteer for a one-way mission to Mars, despite the dangers and hardships. Humans are explorers. It's in our nature. We've spread across every continent on Earth, from the Arctic to the Amazon, from mountaintops to desert valleys. We've learned to survive in environments that should kill us. And now we're reaching beyond Earth, testing whether we can survive in space itself. The people who volunteer for interstellar missions will be the latest in a long line of explorers, carrying forward a tradition as old as our species. But there's a difference between crossing the Pacific and crossing interstellar space. The Polynesians could carry seeds and animals, could establish self-sufficient colonies on the islands they found. Pioneers could hunt, farm, build with local materials. An interstellar crew can't do any of that. They're utterly dependent on their spacecraft and its systems. If the life support fails, they die. If the fusion reactor breaks down, they die. If the food production system fails, they starve. There's no living off the land in interstellar space because there is no land. Just vacuum and radiation. This dependence creates psychological stress. Studies of astronauts on long-duration missions, like year-long stays on the International Space Station, show that isolation and confinement take a toll. Astronauts report feeling disconnected from Earth, frustrated by the inability to simply walk outside, exhausted by the constant vigilance required to maintain complex systems. And that's for missions lasting months or a year or two. What about 40 years? Or 400? You'd need extensive psychological screening for crew members. Training in stress management, conflict resolution, coping strategies. You'd need activities to break the monotony, to give people purpose and meaning beyond just maintaining the ship. Maybe art, music, storytelling. Maybe research projects, studying the interstellar medium during the journey, monitoring the crew's own biology and psychology as data for future missions. Maybe education, with experienced crew members teaching younger ones, passing on knowledge and skills. And you need social structures. Rules for governance, for making decisions, for resolving disputes. On a small ship with a small crew, you can't afford conflicts to fester. You can't have factions forming or power struggles. Everyone needs to work together, cooperate, compromise. That requires leadership, but also buy-in from every crew member. It requires a shared sense of purpose, a collective commitment to the mission. Maybe you select crew members who are already bonded. Families, perhaps. A crew composed of several multi-generational families might maintain cohesion better than a group of unrelated individuals. There's built-in support, built-in relationships. Children grow up in a stable environment, learn from their parents and grandparents. But this also concentrates risk. If one family experiences tragedy, disease, or conflict, it affects a significant portion of the crew. Or maybe you go the opposite direction. Select individuals specifically for their compatibility, their ability to work in teams, their flexibility and resilience. Train them together for years before launch, building bonds and trust. Create an artificial family, a chosen family, united by shared goals rather than genetics. There's no easy answer. Both approaches have merit and risks. The truth is, we won't know what works until we try. And that means the first interstellar crews will be guinea pigs, testing not just the technology but the social and psychological systems needed for long-duration spaceflight. Now let's consider what happens when they arrive. Assuming everything goes perfectly, assuming the ship survives the journey, the crew remains healthy and cohesive, and Proxima Centauri turns out to have something worth studying. What then? If it's an unmanned probe, the mission is relatively straightforward. Study the system, collect data, transmit it home. Maybe the probe carries smaller subprobes that can land on Proxima b, collect samples, analyze the surface and atmosphere. Maybe it includes telescopes to study other objects in the system, asteroids or comets that might tell us about the system's formation. All this data gets beamed back to Earth over the 4.2-year lag. But if it's a crewed mission, things get more interesting. Now you have human judgment, human curiosity, human decision-making. The crew can adapt their mission plan based on what they find. If Proxima b is interesting, they can focus their efforts there. If it's boring but another object in the system looks promising, they can redirect. And there's the tantalizing possibility, landing. Sending humans to actually set foot on an alien world. This would be the ultimate culmination of the mission, the moment that justifies all the effort and expense. A human stepping onto the surface of Proxima b, looking up at a red dwarf sun, seeing truly alien landscapes. Mountains shaped by different geology. Weather patterns driven by tidal locking. A sky that never changes, day never turning to night or vice versa. Colors we can't imagine, chemistry we've never encountered, and maybe, just maybe, life. But landing comes with enormous risks. We don't know what's on the surface. The ground could be solid rock, or it could be quicksand like regolith that swallows landers. The atmosphere could be breathable, or it could be toxic. There could be native microbes that infect humans, or human microbes could contaminate the pristine environment, destroying the very life we came to study. Planetary protection protocols would be essential. Quarantine procedures. Careful sterilization of equipment. Extensive study from orbit before any landing attempt. And even if you land successfully, can you return to orbit? Or is this a one-way trip? With conventional rockets, you need fuel for both descent and ascent. That's heavy. Maybe you use in-situ resource utilization, manufacturing fuel from local materials, but that requires industrial equipment, power systems, time. It's not simple. Perhaps the first landing is robotic, with the human crew remaining in orbit, directing operations remotely. Less risk, but also less discovery potential. Robots can't make the intuitive leaps that humans can. They can't spot the subtle signs of life that a trained biologist might notice. They can't feel the wind, smell the air, sense the character of a place in the way that humans do. These are the trade-offs. Risk versus reward. Safety versus discovery. Every decision carries consequences, and in interstellar space, 4.2 light-years from home, those consequences are magnified. There's no rescue. No second chances. You succeed or you don't. You survive or you don't. Let's zoom out again and think about the bigger picture. Why are we contemplating this journey? What drives us to consider spending trillions of dollars, dedicating generations of effort, risking human lives, all to visit a star system that's probably not that different from billions of others in the galaxy? One answer is simple curiosity. Humans are curious by nature. We want to know what's out there. We want to see things no one has seen before. This curiosity has driven every great exploration in history, from the first humans leaving Africa to the first astronauts landing on the moon. Proxima Centauri is simply the next destination, the next frontier. Another answer is survival. Earth won't last forever. Not because of anything we do, although climate change and environmental destruction certainly threaten our immediate future. But in the long term, truly long term, Earth is doomed. The sun is gradually brightening as it ages, and in about 1 billion years, Earth will become too hot for life. The oceans will evaporate, the atmosphere will be stripped away, and Earth will become a desiccated rock like Venus. If humanity wants to survive beyond that timescale, we need to leave. We need to become a multi-planet species, then a multi-star species. Proxima Centauri is the first step. If we can reach it, if we can establish a presence there, we prove that interstellar colonization is possible. We open the door to spreading throughout the galaxy. And with thousands, millions of human settlements on worlds around different stars, our survival as a species becomes virtually assured. No single catastrophe, no asteroid impact or supervolcano eruption or nuclear war could wipe us all out. But there's a darker implication here. If we spread throughout the galaxy, we inevitably encounter other life. Maybe just microbes. Maybe something more. And history shows that when a technologically advanced civilization encounters a less advanced one, it doesn't usually go well for the less advanced. Europeans colonizing the Americas brought disease, warfare, and cultural destruction to the native populations. If we find life on Proxima b, even microbial life, what responsibility do we have to preserve it? To not contaminate it? To not destroy it in our rush to establish a human presence? These are ethical questions without clear answers. Some argue that human survival and expansion are paramount, that we shouldn't let concern for hypothetical alien microbes prevent us from securing our future. Others argue that we have a moral obligation to any life we encounter, that the universe is rare and precious enough that we should tread lightly, explore gently, preserve what we find. There's a philosophical concept called the Fermi paradox that's relevant here. Enrico Fermi, the physicist, famously asked, "Where is everybody?" If the universe is billions of years old, and there are billions of stars in our galaxy alone, and many of those stars have planets, and some of those planets must be suitable for life, then where are the aliens? Why haven't we detected any sign of extraterrestrial intelligence? Many answers have been proposed. Maybe life is incredibly rare. Maybe intelligence is even rarer. Maybe civilizations tend to destroy themselves before achieving interstellar travel. Maybe space is just too big, and we're all too far apart to ever notice each other. Or maybe advanced civilizations are out there, but they're deliberately hiding, staying quiet to avoid attracting attention from potentially hostile neighbors. If we fly to Proxima Centauri, we're testing some of these hypotheses. If we find life, even simple life, it suggests that life is common in the universe. If we find nothing, it suggests life is rare. Either answer is profoundly important. Either answer changes how we think about our place in the cosmos. And if we do find intelligent life? That's the scenario that keeps philosophers and scientists up at night. First contact. Meeting another civilization, another mind that evolved under completely different circumstances. What do we say? How do we communicate? What do we do if they're hostile? Or if we're accidentally hostile to them? Science fiction has explored these scenarios endlessly. Sometimes first contact goes well, with peaceful exchange of knowledge and culture. Sometimes it goes badly, with war and destruction. Real life is likely to be more complex and ambiguous than either extreme. But the point is, by venturing to Proxima Centauri, we're opening ourselves to possibilities we can barely imagine. Let me tell you about time. Because there's an aspect of interstellar travel we haven't fully explored yet: time dilation. Einstein's special relativity tells us that time passes differently for objects moving at high speeds relative to each other. This isn't science fiction. It's established physics, confirmed by countless experiments. GPS satellites, for instance, have to correct for relativistic effects, or they'd quickly give inaccurate positions. At low speeds, the effects are tiny, negligible. But as you approach the speed of light, they become significant. For an object moving at 50% light speed, time passes about 15% slower than for a stationary observer. At 90% light speed, time passes less than half as fast. At 99.9% light speed, time slows by a factor of about 22. This creates a strange asymmetry. For the crew of a spacecraft traveling at high relativistic speeds, the journey might take decades. But for people on Earth, much more time passes. And vice versa, when the crew looks back at Earth, they see time moving slowly there, while from Earth's perspective, time on the ship is moving slowly. It's reciprocal and weird and completely counterintuitive. At 10% light speed, the relativistic effects are minor. Only about 0.5% time dilation. But if we could somehow build a spacecraft that reaches 90% light speed, the journey to Proxima Centauri would take about 2 years from the crew's perspective, but 5 years from Earth's perspective. If you could reach 99% light speed, the crew experiences about 7 months, while Earth experiences 5 years. This opens up a provocative possibility. If you want to explore the galaxy, really explore it, visiting multiple star systems, you don't need to solve the problem of human aging. You just need to go really, really fast. Time dilation becomes your ally. You could visit dozens of stars, spending decades of subjective time, while centuries pass on Earth. You return to find everyone you knew long dead, civilization transformed beyond recognition, but you've barely aged. This is both a solution and a problem. A solution because it makes extensive exploration possible within a human lifetime, at least from the traveler's perspective. A problem because it severs you from your home. You become unstuck in time, and relic from the past visiting the future. Your family, your friends, your entire culture gone. Replaced by strangers who view you as a historical curiosity. Would anyone volunteer for that? Probably. There are always people willing to sacrifice personal connections for the sake of discovery, for the chance to see and do things no one else has. But it's a sacrifice that should not be underestimated. And this assumes we can reach 90% light speed, which, as we've discussed, is incredibly difficult. The energy requirements scale with velocity, and as you approach light speed, they approach infinity. There's a hard limit at exactly light speed, where the energy required becomes truly infinite. You can get arbitrarily close, 99%, 99.9%, 99.99%, but you can never quite reach 100%. Light speed is the cosmic speed limit, and nothing with mass can reach it. Photons can travel at light speed, but only because they have zero rest mass. Anything with mass, even a single electron, cannot. This is a fundamental constraint of the universe, as far as we know. And it means that interstellar travel will always take time. Always involve crossing vast distances at speeds that, however impressive by human standards, are still a tiny fraction of light speed. Let's come back to Proxima Centauri specifically. What do we actually know about this system? Beyond the basic facts I mentioned earlier, there's a lot we've learned in recent years. Proxima Centauri is what's called a red dwarf, spectral class M5. It's cool, about 3000 Kelvin at its surface compared to the Sun's 5700 Kelvin. It's small, about 1.5 times the diameter of Jupiter, or about 1/7 the diameter of the Sun. And it's dim, really dim, emitting only 0.17% as much light as the Sun. If you were standing on Proxima b, the star would look large in the sky because you're so close to it, but it would be a dull red glow, not the brilliant yellow-white blaze of our Sun. It would be like permanent twilight, that dusky light just after sunset, or just before dawn. Red dwarfs like Proxima Centauri are the most common type of star in the galaxy. About 70% of all stars are red dwarfs. They're also the longest-lived stars. Because they're so cool, they burn their hydrogen fuel very slowly. The Sun will last about 10 billion years total before exhausting its fuel. Proxima Centauri will last about 4 trillion years. That's 4,000 billion years. The current age of the universe is only 13.8 billion years. Proxima Centauri will still be shining long after the Sun has died, long after every other type of star has burned out. Red dwarfs will be the last lights in a darkening universe. This longevity is appealing from a colonization perspective. If you establish a civilization around a red dwarf, you have trillions of years of stable energy output. No worries about your star going supernova or expanding into a red giant and engulfing your planet. Red dwarfs just keep burning, steady and reliable. But there's a downside: flares. Red dwarfs are extremely active, particularly young ones. They produce stellar flares, sudden eruptions of energy and radiation, far more frequently and intensely than the Sun. Proxima Centauri is known for this. In 2017, astronomers observed a flare from Proxima Centauri that increased its brightness by a factor of nearly 70 for a brief period. The flare released an enormous burst of X-rays and ultraviolet radiation, the kind that strips away atmospheres and damages DNA. If Proxima b has a strong magnetic field, like Earth's, it might be protected. The magnetic field would deflect charged particles from the flare, creating auroras but preventing most radiation from reaching the surface. But if Proxima b doesn't have a magnetic field, if it's tidally locked and its rotation has slowed to the point where its dynamos shut down, then every flare bathes the surface in deadly radiation. This is one of the big unknowns about Proxima b. We can detect the planet's presence by measuring the slight wobble it causes in the star's motion as it orbits. We can estimate its mass and orbital period. But we can't yet detect a magnetic field. We can't directly image the surface. We can only speculate, based on models and comparisons with other planets, about what conditions are actually like there. In 2020, astronomers announced the possible detection of a second planet in the Proxima Centauri system, dubbed Proxima c. This one is farther out, possibly a super-Earth or mini-Neptune orbiting every 5.2 years. It's likely too cold for liquid water, too far from the star. But its existence hints that Proxima Centauri might have multiple planets, maybe even a whole planetary system waiting to be discovered. And there's another intriguing detail. Proxima Centauri is part of a triple star system. It orbits the binary pair Alpha Centauri A and B, which are both Sun-like stars, at a distance of about 13,000 astronomical units. That's a huge distance, about 400 times farther than Neptune is from the Sun. From Proxima Centauri, Alpha Centauri A and B would appear as two bright stars, much brighter than any star in Earth's sky, bright enough to cast shadows at night. Could there be planets around Alpha Centauri A and B as well? Possibly. These stars are more similar to the Sun, which means any habitable planets would be in wider orbits, easier to detect with current technology. But their binary nature complicates things. Planetary orbits and binary systems need to be either very close to one star, inside the stable zone, or very far from both, outside the region where their mutual gravity causes chaos. Finding a habitable planet in that configuration is tricky. Still, the possibility exists. If you fly to the Alpha Centauri system, you're not just visiting one star. You're visiting three, potentially with multiple planets. It's an entire stellar neighborhood, our closest cosmic neighbors, waiting for us to drop by. Let's talk about communication. Because even if you successfully reach Proxima Centauri, even if you find something amazing, you need to tell Earth about it. And that's not trivial. Radio waves travel at light speed, which means a signal from Proxima Centauri takes 4.2 years to reach Earth. That's the one-way trip. If you send a message and expect a reply, you're looking at 8.4 years round trip. This makes real-time conversation impossible. Every exchange takes nearly a decade. Imagine the frustration. You discover something incredible, something that raises 1,000 questions. You transmit your findings. You wait. For years pass. Finally, Earth's response arrives. But by then, you've moved on, learned more, your questions have changed. Earth's response addresses your old questions, not your current ones. You send another message. Another 4-year wait. It's like trying to have a conversation with a 4-year delay between each sentence. This latency fundamentally changes the nature of exploration. The crew at Proxima Centauri can't rely on expertise from Earth. They can't phone home when they encounter a problem and expect timely advice. They're on their own. They need to be self-sufficient, capable of making decisions independently, solving problems with the resources and knowledge they have on hand. This is very different from how we conduct space exploration today. When the Mars rovers encounter an unexpected situation, engineers on Earth analyze the data, debate solutions, upload new instructions. The process takes days, but it works because Mars is only light minutes away. Commands uploaded in the morning arrive at Mars before lunch. Proxima Centauri? Your morning commands arrive after your grandchildren have grandchildren. So the spacecraft needs to be autonomous, or crewed by people capable of handling anything that comes up. Extensive training. cross-training in multiple disciplines. Every crew member needs to be a bit of a generalist, able to step in when specialists are unavailable. You need doctors who can handle everything from broken bones to mental health crises. Engineers who can repair any system. Scientists who can adapt their experiments based on unexpected discoveries. And you need data storage. Lots of it. You can't transmit everything back to Earth in real time. The bandwidth isn't there. Even with a powerful transmitter and a receiver the size of a city on Earth, you're limited by the inverse square law. Radio signals spread out as they travel, getting weaker with distance. By the time a signal from Proxima Centauri reaches Earth, it's incredibly faint, requiring massive dishes and sensitive receivers to detect. The solution is data compression and selective transmission. You send the highlights, the most important findings, compressed as tightly as possible. The full dataset, terabytes or petabytes of raw sensor readings, images, video, scientific measurements, stays on the spacecraft. Maybe you send it later, over years of continuous transmission. Maybe you never send it all. Maybe the only way to get the complete data back to Earth is to physically return the spacecraft, or at least its data storage, which brings us full circle to the problem of deceleration and return journeys. Some mission concepts skip the return entirely. One-way trips. The data gets transmitted, but the spacecraft and crew stay at Proxima Centauri. Maybe they establish a permanent outpost. Maybe they explore further, using Proxima Centauri as a staging point for missions deeper into the galaxy. The first interstellar mission becomes the seed for a new branch of human civilization, separated from Earth not just by distance but by time and culture. This raises profound questions about identity. Are the people at Proxima Centauri still human? Biologically, yes. Culturally? After generations of separation, probably not in any way we'd recognize. They'd develop their own traditions, their own values, their own way of seeing the universe. They'd be our descendants, but also something new. The first post-human civilization. Or perhaps the first extraterrestrial human civilization, which is almost the same thing. Let me tell you about the economics. Because someone has to pay for all this, and the cost of an interstellar mission would be unlike anything humanity has ever attempted. The Apollo program cost about $25 billion in the 1960s and 70s, equivalent to about $250 billion in today's dollars when adjusted for inflation. That bought us 12 people walking on the moon, 6 successful landings, and a leap in technology and national prestige that defined a generation. An interstellar mission would cost more. Much more. Orders of magnitude more. We're talking trillions of dollars spread over decades of development. The fusion reactor alone might cost hundreds of billions to develop, test, and flight qualify. The spacecraft itself, assembled in orbit, could run another trillion. The launch infrastructure, the training facilities, the mission control systems, the deep space communication network, all add up. Where does this money come from? No single nation can afford it, not without sacrificing other priorities like healthcare, education, infrastructure. You'd need international cooperation on a scale never before achieved. The International Space Station cost about $150 billion and involved 15 countries. An interstellar mission would need even broader participation. Maybe a United Nations interstellar initiative. Maybe a consortium of spacefaring nations pooling resources. Maybe private corporations and billionaires with visions of cosmic expansion. And what's the return on investment? You can't really measure it in dollars. There's no profit, at least not in the traditional sense. No resources to extract and bring back to Earth. No real estate to develop and sell. The return is knowledge, prestige, and the long-term survival of our species. Important, yes, but hard to quantify on a balance sheet. History provides some guidance. Great explorations were often funded by monarchs or governments seeking prestige and power. The Spanish funded Columbus not because they expected immediate profit but because they wanted to compete with Portugal in finding new trade routes. The space race happened because the United States and Soviet Union were competing for technological and ideological supremacy. Money flowed because the stakes, in terms of national pride and global influence, were high. Maybe an interstellar mission requires similar motivations. A new space race, but this time the finish line is Proxima Centauri. Competing nations or blocks racing to be first to another star. The prestige of achieving that goal, the technological spin-offs, the inspiration to younger generations, might justify the expense in political terms if not purely economic ones. Or maybe the motivation comes from existential risk. If humanity faces a credible threat, an asteroid impact, a gamma ray burst, a pandemic that could wipe us out, suddenly the cost of interstellar insurance looks more reasonable. Establishing a backup civilization at Proxima Centauri guarantees that humanity survives even if Earth doesn't. How much is that worth? Everything, arguably. Let's consider the timeline. When could we actually do this? When could we launch a mission to Proxima Centauri? With current technology, never. We simply don't have the propulsion systems, the energy sources, or the life support systems needed. But technology advances. Sometimes slowly, sometimes in sudden leaps. Predicting when a breakthrough will happen is notoriously difficult. Fusion power has been 30 years away for the past 60 years. But recent progress, from projects like ITER and private ventures like Commonwealth Fusion Systems, suggests we might actually be getting close. If fusion becomes practical in the 2030s or 2040s, and if we can miniaturize and ruggedize it for spaceflight by the 2060s or 2070s, then we might have the propulsion technology needed. Life support is easier. We're already testing closed-loop systems on the ISS, recycling air and water with high efficiency. Scaling these up for longer missions is an engineering challenge, not a physics challenge. Growing food in space, under artificial light, is being demonstrated on the ISS and will be tested further on lunar bases and Mars missions. The harder parts are the social and political will. Convincing governments to spend trillions. Maintaining public support over the decades required for development. Coordinating international efforts without getting bogged down in politics and rivalry. Optimistically, if we started serious development today, we might launch a probe, a small unmanned mission using light sail technology or advanced ion drives, by the 2050s or 2060s. A crewed mission would take longer, probably not before the 22nd century. But here's the thing, we don't need to wait. Even if we can't send people, we can send information. We can study Proxima Centauri with increasingly powerful telescopes. The James Webb Space Telescope, launched in 2021, can study the atmospheres of exoplanets, looking for chemical signatures of life. Future telescopes, larger and more sensitive, will be able to directly image planets like Proxima b, see their surfaces, map their features. We might answer the question, is there life on Proxima b? Without ever going there. We might see cities, if there's an advanced civilization. We might detect industrial pollution, radio signals, signs of technology. Or we might see a lifeless rock and decide the journey isn't worth it. This is the paradox of interstellar exploration. The better our remote sensing becomes, the less urgency there is to actually go. Why risk human lives and spend trillions when you can get most of the scientific value from telescopes? The counterargument is that there are things you can only learn by being there. Subtleties that sensors can't detect. Serendipitous discoveries made by humans on the ground. And the intangible value of the journey itself, the human experience of standing on another world. I think both are valid. We should absolutely build better telescopes, study exoplanets remotely, gather as much data as we can. But we should also plan for eventual direct exploration. Because ultimately, humans are explorers. We don't just want to know what's out there. We want to go there. We want to touch it, walk on it, experience it firsthand. Let's talk about what the journey would actually feel like. Imagine you're a crew member on an interstellar spacecraft. You've trained for years, said your goodbyes, boarded the ship. The launch is spectacular, fusion engines igniting with the light of a newborn star, pushing you away from Earth at increasing speeds. For the first weeks, Earth is still visible, a blue marble shrinking behind you. You can still make out continents, oceans, the white swirl of clouds. You watch it every day, a reminder of home. Then one day you look back, and it's just a dot. Another day, and you can't distinguish it from the stars around it. You're beyond the orbit of Mars, then Jupiter, then Neptune. The sun is still bright, but noticeably smaller, no longer the overwhelming presence that dominated Earth's sky. After a year, you've passed the Kuiper Belt, the region of icy bodies beyond Neptune. You're in the Oort cloud now, the vast shell of comets that marks the true boundary of the solar system. The sun is just a bright star, no different from other stars except you know which one it is. You're farther from home than any human has ever been. And you're barely started. The Oort cloud extends halfway to Proxima Centauri. You'll spend another year crossing it. Then you're truly in interstellar space. The sun is behind you, fading. Proxima Centauri is ahead, but it's still just a dot, indistinguishable from countless other dots. This is when the psychological challenge really begins. You're in the empty space between stars, surrounded by darkness. There's nothing to see except stars, unchanging, unmoving. Days blend into weeks, blend into months, blend into years. The ship becomes your entire world. Its corridors, its compartments, its recycled air and humming machinery. You exercise daily to prevent muscle atrophy. You maintain the ship's systems, running diagnostics, performing repairs. You conduct experiments, studying the interstellar medium, measuring cosmic rays, observing distant galaxies. You communicate with Earth, though the time lag grows longer every day. Your messages take months to arrive, and replies take months to return. You're having conversations with the past, sending messages to people who may have moved on, changed, forgotten you. You form bonds with your crewmates. They're the only other humans in existence, as far as your immediate experience is concerned. You celebrate birthdays, holidays, invent new traditions. Maybe you fall in love. Maybe you have children, though the ethics and practicality of that are debatable. Maybe you just become a tight-knit family, supporting each other through the loneliness and monotony. And slowly, imperceptibly at first, Proxima Centauri grows brighter. After 10 years, it's noticeably brighter than when you started. After 20 years, it's the brightest star in your forward view. After 30 years, it's brilliant, a red beacon drawing you onward. And after 40 years, it's not a point anymore. It's a disk. You can see it as an actual object, a star with size and shape. You've arrived. The last few months are the busiest. You need to decelerate, bleeding off the enormous velocity you've built up. The fusion engines, silent for most of the journey, fire again. You feel weight for the first time in decades, pulled toward the aft of the ship by the thrust. It's disorienting, uncomfortable even, after so long in microgravity. As you slow, instruments come online. Telescopes focus on Proxima b, resolving it from a point of light to an actual world. You see color, texture, features. Clouds, if there are any. Oceans, if they exist. Maybe the glint of ice at the poles. Maybe nothing, just bare rock and dust. And then you're there, orbiting Proxima Centauri, looking at an alien world, preparing to explore, to discover, to answer the questions you've carried across 4.2 light-years. What do you find? That's the mystery. That's the whole point. We don't know. We can't know until we go. Maybe Proxima b is a dead world, sterilized by stellar flares, its surface baked and frozen in equal measure. Maybe it's a water world, completely covered by ocean, with life teeming in the depths. Maybe it's Earth-like, with continents and oceans and an atmosphere you could breathe. Maybe there are ruins, the remnants of a civilization that rose and fell millions of years ago. Maybe there's life now, intelligent or otherwise, looking up at the sky and wondering if they're alone. Every outcome is profound. Every outcome changes us. Because by going to Proxima Centauri, by crossing the interstellar gulf, we're not just exploring space. We're exploring ourselves. We're testing our capabilities, our persistence, our courage. We're asking, can we do this? And more importantly, should we do this? I think the answer to both questions is yes. We can, given time and resources and commitment. And we should, because exploration is what we do. It's what defines us as a species. We're curious. We're ambitious. We're restless. We look at the horizon, whether it's the literal horizon of Earth or the cosmic horizon of the visible universe, and we want to see what's beyond it. Flying from Earth to Proxima Centauri is the ultimate expression of that drive. It's a journey that will take generations to prepare, decades to complete, and will yield discoveries we can barely imagine. It's a journey that will test everything we know about physics, engineering, biology, psychology, and sociology. It's a journey that will require cooperation on a global scale, commitment across generations, and courage in the face of enormous risks. But it's a journey worth taking. Because 4.2 light-years away, there's a red dwarf star with at least one planet. And we want to know what's there. We need to know. Not for profit, not for resources, not even for survival, though that's a factor. We need to know because we're human, and knowing is what we do. So we'll build the ships. We'll develop the technology. We'll train the crews. And someday, maybe in our lifetime, maybe in our children's or grandchildren's lifetime, we'll launch. We'll watch as the first human-made object accelerates toward another star, carrying our hopes, our dreams, our curiosity across the cosmic void. And when it arrives, when the first images, the first data, the first signals come back across the 4.2-year gap, we'll know. We'll finally know what's at Proxima Centauri. And we'll start planning the next journey, to the next star, and the next, spreading throughout the galaxy 1 light-year at a time. Because flying from Earth to Proxima Centauri isn't the end of anything. It's the beginning. The first step on a journey that will take us to the stars, and beyond, into a future we can barely imagine but can't wait to discover. That's what flying from Earth to Proxima Centauri means. It's not just a journey across space. It's a journey across time, across possibility, across the boundary between what we are and what we can become. It's humanity reaching out to touch the cosmos and finding that the cosmos reaches back. And when we finally arrive, when we stand on that alien shore and look up at that red sun, we'll realize something profound. We're not visitors. We're not tourists. We're part of this universe, and it's part of us. We came from the stars, literally, our atoms forged in the hearts of ancient supernovas. And now we're returning, coming home to the wider cosmos from which we emerged. Flying from Earth to Proxima Centauri is the story of that return. It's the story of us. And it's a story that's just beginning. The mechanics of actually navigating to Proxima Centauri present challenges that go beyond simple point-and-shoot trajectories. Space isn't static. Everything is moving. Earth orbits the Sun at 67,000 miles per hour. The Sun orbits the galactic center at 500,000 miles per hour. Proxima Centauri has its own motion relative to us, what astronomers call proper motion. It's moving toward us, actually, closing the distance by about 3 miles per second. In 27,000 years, it'll be the closest it ever gets to our solar system, about 3 light-years away. Then it'll start receding again. This motion matters. When you launch toward Proxima Centauri, you're not aiming at where it is now. You're aiming at where it will be 40 years from now. It's like throwing a football to a receiver running downfield. You lead the target. You calculate the intercept point based on both your velocity and the target's velocity. Get it wrong by even a fraction of a degree, and you miss by billions of miles. The navigation computer needs to account for gravitational influences too. The Sun's gravity affects your trajectory, bending your path as you escape the solar system. Jupiter's gravity might give you a slingshot boost if you time your launch right, stealing a tiny bit of the giant planet's orbital momentum to increase your speed. Every object in the solar system tugs at you with its gravity, and while most of these forces are negligible, they accumulate over time. Over 40 years, small errors become large errors. Then there's the galactic environment itself. The Sun travels through different regions of the galaxy, areas with varying densities of interstellar gas and dust. Right now, we're in what's called the local bubble, a region of lower density gas carved out by ancient supernova explosions. But the boundaries of this bubble aren't sharp. There are filaments of denser material, clouds of hydrogen and helium. Your spacecraft might pass through these, experiencing increased drag, more impacts, higher radiation levels. And we need to talk about course corrections. You can't just point the ship and coast for 40 years. Tiny errors accumulate. That dust grain that hit you 5 years into the mission? It knocked you slightly off course. That unexpected solar flare? It gave your magnetic shielding a workout and possibly damaged some sensors. You need to make adjustments. Fire maneuvering thrusters. Recalculate your trajectory. This requires fuel, not much compared to your main engines, but it adds up over decades. The communications challenge extends beyond just lag time. As your distance from Earth increases, the signal strength decreases with the square of the distance. Double the distance, and you need 4 times the power to maintain the same signal strength. By the time you're halfway to Proxima Centauri, 2 light-years out, the signal is 16 times weaker than it was at half a light-year. You compensate with larger antennas, more sensitive receivers, more powerful transmitters. But there are practical limits. Earth-based receivers need to be enormous. We're talking radio dishes hundreds of meters across, like the Arecibo Observatory that collapsed in 2020, or the 500-meter aperture spherical telescope in China. Even then, the signal from Proxima Centauri is so faint it's competing with cosmic background noise, with interference from other stars, with the radio emissions from Jupiter and the Sun itself. Extracting this signal requires sophisticated filtering, error correction codes, multiple redundant transmissions. And the spacecraft's transmitter needs to be aimed with incredible precision. A radio beam spreads out as it travels. By the time it reaches Earth from Proxima Centauri, even a tightly focused beam has spread to cover an area larger than the entire solar system. Most of the energy misses Earth entirely. To maximize the signal strength, you need a high-gain directional antenna pointed exactly at Earth. Exactly? Within fractions of a degree. This requires knowing your position and Earth's position with extreme accuracy, which circles back to the navigation problem. Let's consider the human body in this environment. 40 years is a significant fraction of a human lifespan. People who launch in their 20s arrive in their 60s. They'll experience all the normal effects of aging, but accelerated by the space environment. Bone density loss occurs in microgravity at about 1 to 2% per month without countermeasures. Over 40 years, even with aggressive exercise programs, you're looking at severe osteoporosis. Your bones become brittle, fragile. A fall that would bruise you on Earth could break bones in space. Muscle atrophy is similar. Your heart doesn't need to work as hard pumping blood in microgravity, so it weakens. Your leg muscles, which normally fight gravity every moment you're standing or walking, waste away. Astronauts on the ISS exercise 2 to 3 hours daily just to maintain baseline fitness. For 40 years, you'd need to dedicate significant portions of every day to exercise, and even then, the deterioration continues. Radiation exposure causes different problems. Cosmic rays damage DNA, increasing cancer risk. They also affect the brain. Studies of astronauts show cognitive changes after long-duration missions, possibly due to radiation damage to neurons. Over 40 years, these effects compound. You might arrive at Proxima Centauri physically frail, mentally slower, more prone to memory problems and reduced reaction times. One solution is artificial gravity through rotation. Spin the spacecraft, or a section of it, and centrifugal force creates the sensation of weight. The physics are straightforward. The challenge is engineering. A rotating structure needs to be perfectly balanced, or it wobbles. The rotation rate needs to be slow enough to avoid Coriolis effects that make movement disorienting and nausea-inducing. For comfortable Earth-like gravity, you need either a very large radius, like hundreds of meters, or a higher rotation rate that causes problems. Most designs compromise. Maybe you create partial gravity, 1/3 or 1/2 Earth normal, enough to prevent the worst bone and muscle loss but not enough to require enormous rotating structures. Or maybe you have a small centrifuge that crew members use for exercise and sleep, spending most of their waking hours in microgravity. It's not ideal, but space travel never is. It's always about trade-offs and compromises. Psychological studies of isolated groups suggest other problems emerge over time. Cabin fever, obviously. Depression rates increase in confined environments with limited sunlight and social interaction. Interpersonal conflicts can escalate when there's no escape, no ability to take a break from people you're frustrated with. On Earth, if your coworker annoys you, you go home at the end of the day. In a spacecraft, your coworker is always there, sleeping 20 feet away, eating across from you, working beside you. NASA has studied this extensively through analog missions. The HIC's habitat in Hawaii, the Mars 500 experiment in Russia, various Antarctic research stations. These studies reveal patterns. The first few months are exciting, novel. Everyone is on their best behavior, cooperative, enthusiastic. Then reality sets in. Monotony. Frustration. Small annoyances become major grievances. Some crews handle it well, maintaining cohesion through strong leadership and clear communication. Other crews fracture, forming cliques, withdrawing into isolation. For a 40-year mission, you'd see these cycles repeat many times. Periods of high morale followed by periods of low morale. The arrival of new data from Earth, major mission milestones, successful experiments, these boost spirits temporarily. Equipment failures, bad news from home, health problems, these depress spirits. Managing this psychological roller coaster is as important as managing the technical systems. You'd probably want a trained psychologist as part of the crew. Someone who can provide counseling, mediate conflicts, help people process their feelings. But who counsels the counselor? They're human too, subject to the same stresses and strains. Maybe you rotate the role, train everyone in basic psychological first aid. Or maybe you maintain contact with psychologists on Earth, accepting the multi-month delay in responses. Video messages from a therapist might help, even if they're addressing problems from 6 months ago. Entertainment becomes critical. You need books, movies, music, games, anything to break the monotony. But you can't carry physical media for 40 years' worth of entertainment. Storage space is limited, and mass matters. Digital storage helps, but even then, hard drives fail, data corrupts. You need redundancy, multiple copies of everything. Maybe you establish a shipboard library, carefully curated to provide variety and depth. Classic literature, contemporary fiction, technical manuals, humor, poetry, everything. Creative activities help too. Art, music composition, writing. Some crew members might document the journey, keeping journals or recording video logs. These serve dual purposes, therapeutic for the creator and historical record for everyone else. The journals of early explorers, from Marco Polo to Lewis and Clark, provide invaluable insights into their journeys. The journals from Proxima Centauri would be equally valuable. Education could fill time as well. Crew members teaching each other their specialties. The biologist explains genetics. The physicist describes relativity. The engineer demonstrates propulsion systems. Learning new skills, languages, scientific disciplines, keeps minds active and provides social bonding through shared intellectual pursuits. And there's the possibility of hibernation or suspended animation, though this remains science fiction for now. If you could put crew members into a state of reduced metabolism, slowing their aging and reducing resource consumption, the journey becomes more feasible. Bears hibernate for months, dropping their heart rate and body temperature, surviving on stored fat. Some organisms can enter even deeper states, near suspended animation, remaining viable for years or decades. Humans can't do this naturally, but maybe we could artificially. Cooling the body reduces metabolic rate. Combined with drugs to prevent cell damage, to maintain basic functions, you might achieve something resembling hibernation. Research in this area focuses on medical applications, preserving organs for transplant or stabilizing trauma patients during transport. Extending it to months or years? That's far beyond current capabilities. Even if we could hibernate humans, there are risks. What if the revival process fails? What if you hibernate for 20 years and wake up with brain damage or organ failure? What if the automated systems that monitor your hibernation malfunction, and you die in your sleep? The first tests of human hibernation won't happen on an interstellar spacecraft. They'll happen in controlled laboratory settings, with immediate medical support available. Perfecting the technology will take decades, maybe longer. Let's talk about the composition of the crew. Who goes? What skills do you need? Obviously, you need technical expertise. Engineers to maintain the ship. Scientists to conduct research. Medical personnel to keep everyone healthy. But you also need practical skills. Cooking, agriculture if you're growing food, maintenance and repair, teaching if there are children. Diversity matters too, not just in skills but in perspective. Different cultural backgrounds, different ways of thinking, different problem-solving approaches. A crew drawn entirely from one culture might miss solutions that seem obvious to someone from a different background. And representation is important for public support. This is humanity's mission, not one nation's. The crew should reflect that. Age distribution is another consideration. Do you send young people who live long enough to see the destination but lack experience? Or older, more experienced individuals who might die en route? A mix is probably best. Younger members provide energy and adaptability. Older members provide wisdom and stability. But then you're dealing with generational dynamics, essentially a small society with distinct age cohorts. Selection criteria would be brutal. For every slot on the crew, there'd be thousands of applicants. You'd screen for physical health, mental stability, technical competence, interpersonal skills, adaptability, creativity, all while trying to assemble a balanced team that works well together. The training program would take years, during which some candidates wash out or decide the commitment is too great. And then there's the question of reproduction. Do you allow or encourage crew members to have children? On one hand, children born during the journey are the most adapted to spacecraft life. They'll never know Earth's gravity or atmosphere. The ship is their home, Proxima Centauri their destination. They have a personal stake in the mission's success. On the other hand, children complicate everything. They require resources, attention, education. They didn't choose this life. Is it ethical to bring them into such a confined, risky environment? Some mission plans explicitly include multi-generational crews. Launch with families, plan for population growth, arrive at Proxima Centauri with a larger crew than you started with. This provides genetic diversity if you're planning to establish a colony, and it creates a more natural social structure. But it also increases resource requirements and introduces unpredictability. What if the birth rate is lower than expected? What if it's higher? The ship's design needs to accommodate this. Nurseries, schools, recreational areas for children. Safety features to prevent accidents in an environment full of hazardous equipment. Educational materials to teach everything from basic literacy to advanced science. And somehow, you need to instill in these children, who've never seen Earth, a commitment to completing a mission their ancestors started. Alternative approaches avoid these issues by keeping the crew small and childless. Pure professionals, selected for mission competence, serving their 40 years and never starting families. This maximizes efficiency but creates a different kind of social environment, one that might feel sterile or lonely. Now consider contingencies. What happens if something goes catastrophically wrong? If the fusion reactor fails halfway through the journey, you're stranded in interstellar space with no way to accelerate or decelerate. You're coasting at 10% light speed forever, or until your life support fails, whichever comes first. Do you have a backup reactor? That doubles your mass and complexity. Do you have repair capabilities extensive enough to rebuild major systems? That requires carrying spare parts, raw materials, manufacturing equipment. What if a crew member becomes violently mentally ill? On Earth, we have psychiatric hospitals, medications, therapeutic interventions. In space, you have limited medical supplies and no possibility of evacuation. Restraining someone for their own safety, or the crew's safety, raises ethical and practical questions. The same goes for criminal behavior. If someone sabotages equipment or harms another crew member, what do? There's no prison, no police, no legal system beyond whatever governance structure the crew establishes. These worst-case scenarios require planning, pre-established protocols for emergencies, clear chains of command, ethical guidelines that everyone agrees to before launch. But no amount of planning covers every possibility. At some point, the crew needs discretion to handle situations as they arise, trusting their judgment and hoping they make the right calls. Consider the information the spacecraft carries. It's not just a vehicle, it's an ark of human knowledge. If something were to happen to Earth, if civilization collapsed or humanity went extinct, this spacecraft might be the only surviving record of what we were. So you'd want to include comprehensive archives. Literature, art, music, scientific knowledge, historical records. The whole of human achievement, compressed into whatever data storage you can spare. The Voyager spacecraft carried golden records. Phonograph records with sounds and images from Earth. A message to any alien intelligence that might find them billions of years from now. A Proxima Centauri mission would carry something similar but vastly more extensive. Terabytes or petabytes of data. Everything from Shakespeare to quantum physics, from Beethoven to genomic databases. But you also carry the contamination question. We've worried about this with Mars. If we bring Earth microbes to Mars, we might accidentally seed the planet with life, making it impossible to tell if Mars ever had its own native biology. Proxima Centauri is far enough away that cross-contamination seems unlikely, but it's not impossible. If your spacecraft crashes or leaks, could Earth microbes survive and spread? Probably not. The conditions on most exoplanets are so hostile that Earth life wouldn't stand a chance. But extremophiles, organisms that thrive in harsh conditions, might. Tardigrades can survive in space, withstand radiation, endure freezing and desiccation. If tardigrades hitched a ride to Proxima b and somehow found a hospitable microenvironment, could they establish a population? It seems far-fetched, but biology is full of surprises. Planetary protection protocols would require strict sterilization. Every surface of the spacecraft, every tool, every sample container, sterilized before launch and maintained sterile throughout the journey. But humans are walking ecosystems, carrying trillions of microbes in and on our bodies. You can't sterilize the crew. So some level of contamination is inevitable if you're sending people. This tension between exploration and preservation doesn't have easy answers. We want to study alien environments in their pristine state, but our presence inherently alters them. Maybe the solution is to conduct initial studies with robotic probes, thoroughly characterize the environment, and only send humans after we understand what we're dealing with. Or maybe we accept that some level of contamination is unavoidable and focus on minimizing it rather than eliminating it entirely. The legal framework for interstellar travel doesn't exist yet. Who owns Proxima Centauri? Can a nation claim it? Can a corporation? The Outer Space Treaty of 1967 prohibits national appropriation of celestial bodies, but it was written in the context of the moon and planets in our solar system. Does it apply to other star systems? Probably in spirit if not letter, but there's no enforcement mechanism and no precedent. If we establish a colony at Proxima Centauri, what's its legal status? Is it a territory of Earth nations that funded the mission? Is it independent? Do the colonists have representation in Earth governments, or do they govern themselves? With an 8-year round-trip communication delay, practical self-governance is almost mandatory. You can't rule from Earth when instructions take 4 years to arrive and confirmations take another 4 to return. This could lead to the first truly independent human society beyond Earth. A government formed from scratch, not constrained by Earth's historical baggage, free to experiment with new social structures. Maybe they develop something better than what we have on Earth. Maybe they repeat our mistakes. Either way, it would be a fascinating experiment in political science, sociology, and human nature. Trade between Earth and Proxima Centauri is essentially impossible under conventional physics. 8 years for a message means decades for physical goods. What could possibly be worth shipping across that distance and delay? Information is the only practical commodity. Scientific data, cultural products, ideas. These transmit at light speed and have no mass. Everything else is too expensive, too slow, too impractical. Unless you crack faster-than-light communication, which is even more speculative than faster-than-light travel. Quantum entanglement doesn't allow FTL communication despite popular misconceptions. Wormholes are theoretically possible in general relativity but require exotic matter to hold them open. Tachyons, hypothetical faster-than-light particles, might exist but probably don't and wouldn't help anyway. So the Proxima Centauri colony, if established, would be economically independent from Earth by necessity. They need to be self-sufficient, producing everything they need locally. Mining asteroids or moons for raw materials. Manufacturing in zero gravity. Developing agriculture suitable for their environment. It would be harder than any Earth settlement, because unlike pioneers who could at least breathe the air and find water, space colonists need to create every aspect of their environment from scratch. The cultural divergence would be rapid. Within a few generations, Proxima Centaurians would develop their own identity, distinct from Earth. Their language would drift, incorporating new words for new concepts, dropping archaic terms. Their customs would evolve in response to their unique environment. Their values might shift, prioritizing cooperation and technical competence over other traits. They'd remember Earth as their origin but not as their home. And from Earth's perspective, Proxima Centauri becomes a reflection of what we once were. The colony preserves a snapshot of early 22nd century or whenever culture while Earth continues evolving. When communication finally arrives, both sides would find the other strangely antiquated or alien. The Proxima Centaurians might seem quaint, still using technology and speaking in ways Earth has moved beyond. Or they might seem advanced, having developed solutions to problems Earth still struggles with. This is the nature of relativistic colonization. Not just crossing space but crossing time, creating divergent branches of humanity that grow apart with each passing year. Let's return to the question of velocity. 10% light speed gets you there in 43 years. 20% cuts that to 22 years. 50%, just 9 years. But the energy requirements scale roughly with the square of velocity. Doubling your speed requires 4 times the energy. Quintupling your speed requires 25 times the energy. At some point, you hit diminishing returns where the benefit of faster travel doesn't justify the exponentially increasing cost. There's also a practical limit on how fast you can safely travel through the interstellar medium. Remember those hydrogen atoms we discussed? At 10% light speed, they're dangerous. At 50% light speed, they're lethal. Each atom hits with 16 times more energy. That dust grain that was equivalent to dynamite? Now it's equivalent to a small nuclear weapon. Your shielding requirements increase dramatically. Some theoretical designs address this with active shielding. A magnetic field projected ahead of the spacecraft deflects charged particles. A laser or particle beam vaporizes incoming dust grains before they reach the ship. A plasma cloud pushed forward catches debris and ablates gradually, sacrificing itself to protect the main ship. All of these require energy, significant energy, which adds to your propulsion requirements. There's a sweet spot somewhere in the 10 to 20% light speed range where travel time is reasonable and energy requirements are achievable with foreseeable technology. Going faster is possible but extraordinarily difficult. Going slower saves energy but extends mission duration to the point where multi-generational crews or hibernation become necessary. What about using the sun itself as an energy source? The sun outputs about 3.8 times 10 to the 26th watts of power. That's an incomprehensibly large number. If you could capture even a tiny fraction of that power, you'd have more than enough to accelerate a spacecraft to relativistic speeds. This is the concept behind a Dyson swarm, thousands or millions of solar collectors orbiting the sun, harvesting its energy. Building a Dyson swarm is a massive undertaking, requiring asteroid mining on an industrial scale, autonomous construction robots, decades of work. But once built, it provides essentially unlimited energy for civilization's needs, including interstellar missions. The swarm could power massive laser arrays for light sail propulsion, or charge enormous capacitor banks that discharge into electromagnetic catapults that fling spacecraft toward other stars. This is thinking on a civilization scale, not a single mission scale. But that's perhaps what interstellar travel requires. Not just one spacecraft to Proxima Centauri, but the infrastructure to support regular missions, multiple destinations, a sustained presence in interstellar space. Building that infrastructure takes generations, but it enables activities that would be impossible otherwise. And once you have the infrastructure, the missions become routine. Not easy, but routine. The first voyage to Proxima Centauri is an epic feat, but the 10th? The 100th? They're still dangerous, still challenging, but they're known quantities. You have experience, refined procedures, proven technology. Just like how commercial air travel today is routine, even though the Wright brothers' first flight was a historic breakthrough. The end game is humanity as a spacefaring species, not just confined to one planet or one star system but spread throughout the galaxy. Multiple colonies around multiple stars, linked by slow communication and occasional trade of information. Each colony adapted to its local environment, each developing its own culture, but all sharing a common origin and a common identity as human. Getting there requires starting somewhere. And Proxima Centauri, our nearest stellar neighbor, is that starting point. 4.2 light-years away. Close enough to be achievable with foreseeable technology. Far enough to require solving all the fundamental challenges of interstellar travel. It's the perfect first step. When we finally make that journey, when the first spacecraft enters orbit around Proxima Centauri and begins transmitting its findings back to Earth, that will be the moment everything changes. Not just for the crew, not just for the scientists analyzing the data, but for all of humanity. Because we'll have proven that the stars aren't unreachable. The galaxy isn't forever beyond our grasp. We can go there. We can explore. We can expand. And that realization, that shift in perspective from earthbound to starfaring, will fundamentally transform how we think about ourselves and our place in the universe. We're not isolated on a single planet orbiting a single star. We're children of the cosmos, capable of returning to the stars that gave us birth. Flying from Earth to Proxima Centauri is how that transformation begins. The engineering reality of building such a spacecraft forces us to confront material science at its limits. Every component needs to function flawlessly for decades in conditions we can barely simulate on Earth. The whole material must withstand micrometeorite impacts, thermal cycling from extreme cold to intense heat near the engines, and radiation exposure that would turn most metals brittle over time. Aluminum, the go-to material for spacecraft, becomes brittle when bombarded with high-energy particles. Steel is stronger but heavier. Titanium offers a good compromise but is expensive and difficult to work with. Advanced composites might be the answer. Carbon fiber reinforced polymers, boron nitride nanotubes, graphene-based materials. These offer incredible strength-to-weight ratios and can be engineered to resist radiation damage better than metals. But they're largely untested in long-duration space applications. The ISS has been in orbit for over 2 decades, and we've learned that materials behave differently in space than on Earth. Plastics that are flexible on the ground become rigid and crack in the cold vacuum. Lubricants evaporate. Seals degrade. Everything ages in unexpected ways. For a 40-year mission, you need materials that won't just survive but remain reliable. This means extensive testing, accelerated aging studies, real-world validation in space before committing to a design. You might establish a test article in solar orbit, exposing sample materials to the space environment for years, monitoring their degradation, refining your selections based on actual performance rather than laboratory predictions. The power systems present their own constellation of problems. Solar panels work near Earth where sunlight is abundant, but beyond Mars, the sun's intensity drops dramatically. By the time you're in interstellar space, solar power is useless. You need something that generates power without external energy sources. Radioisotope thermoelectric generators, like those powering the Voyager probes, use the heat from radioactive decay to generate electricity. They're reliable and long-lasting, but they produce relatively little power, only hundreds of watts. For a crewed mission with extensive life support, communications, and propulsion needs, you need kilowatts or megawatts. That means a nuclear reactor. Not the massive reactors that power cities on Earth, but compact, space-rated designs that can operate for decades without refueling. The Soviet Union flew nuclear reactors on satellites in the 1970s and 80s. NASA developed designs in the 1960s for nuclear rockets. But flying a reactor with a human crew nearby requires solving safety issues that have kept nuclear power out of most space applications. Shielding is paramount. The reactor core emits neutrons and gamma rays that are lethal to humans. You need meters of shielding, or you need distance. Put the reactor on a long boom, hundreds of meters from the crew compartment, so the radiation drops to safe levels before reaching people. But long booms are structurally challenging, especially if they need to handle the thrust loads from engines mounted at the far end. Reactor cooling is another issue. On Earth, reactors use water or air to carry heat away. In space, you can't dump heat into water or air. You need radiators, large surfaces that radiate heat away as infrared light. These radiators are vulnerable to micrometeorite damage and need to be sized appropriately for the reactor's heat output. A megawatt reactor might need radiators covering hundreds of square meters. Redundancy becomes critical when you're years away from any repair facility. If a critical system fails, you can't call for a replacement part or a service technician. You fix it yourself or you die. This means carrying spares for everything, multiple backups for critical systems, and tools and materials to fabricate parts you didn't anticipate needing. Three-dimensional printing helps. Modern 3D printers can work with metals, plastics, ceramics, even biological materials. Given the right raw materials and the digital design files, you can manufacture replacement parts on demand. This reduces the need to carry physical spares for every possible component, though you still need raw materials in various forms. But 3D printing has limitations. The parts aren't always as strong as traditionally manufactured components. Complex assemblies with tight tolerances are difficult to print correctly. And you need power, lots of it, to run the printers. For metal printing, you're melting or sintering metal powders with lasers or electron beams, processes that consume kilowatts per hour. Self-repair capabilities might extend to biological systems too. If you're growing food hydroponically, you're essentially running a controlled ecosystem. Plants clean air by absorbing carbon dioxide and releasing oxygen. They provide food and psychological benefits, greenery in an otherwise sterile metal environment. But plants are finicky. They need the right light spectrum, the right nutrients, the right temperature and humidity. Disease can wipe out crops. Pests, if they somehow sneak aboard, can devastate your food production. You need agricultural expertise in the crew, someone who understands plant biology, who can diagnose problems and implement solutions. You need backup seeds, stored properly to remain viable for decades. You need the ability to crossbreed and adapt crops to the artificial environment, essentially conducting agricultural evolution in real time. Closed-loop life support aims for perfect recycling, but perfect is impossible. There are always losses. A little oxygen here, a little water there. Over 40 years, these losses add up. You need reserves, buffers to handle the gradual depletion. And you need ways to reclaim materials from waste. Human waste contains water, nitrogen, phosphorus, nutrients that plants need. Recycling this waste is both practical and psychologically challenging. People need to accept that the water they drink today might have been urine last week. The ISS recycles about 93% of its water. The remaining 7% is lost to inefficiencies in the system and to vapor that escapes when cargo vehicles dock and undock. On an interstellar mission, you can't afford 7% losses. You need to push recycling efficiency higher, maybe 99% or better. That requires more sophisticated processing, more energy, more maintenance. Air recycling faces similar challenges. The ISS uses a system that scrubs carbon dioxide from the air and combines it with hydrogen to produce water and methane. The methane is vented to space, which represents a loss of hydrogen. A closed system would need to crack the methane back into hydrogen and carbon, recycle both, achieve true closure. Such systems exist in concept but haven't been tested at scale in space. Food production, water recycling, air regeneration, these aren't independent systems. They're interconnected, forming an artificial ecosystem. The plants need water, which comes from the recycling system. They produce oxygen, which the crew breathes. The crew exhales carbon dioxide, which the plants use for photosynthesis. Waste from the crew fertilizes the plants. It's a cycle, and breaking any link in the cycle threatens the whole system. Balancing this ecosystem is delicate work. Too many plants and you generate excess oxygen, which is a fire hazard. Too few and carbon dioxide builds up, which is toxic. The nutrient levels in the water need to be monitored and adjusted constantly. The pH, the temperature, the light intensity, all affect plant growth and system stability. It's like maintaining an aquarium, but the aquarium is keeping you alive. Now think about the data management requirements. Sensors throughout the spacecraft are constantly collecting information. Temperature, pressure, radiation levels, oxygen concentration, power output, fuel levels, structural strain, equipment status. Thousands of data points, sampled multiple times per second. This generates enormous amounts of data that need to be stored, analyzed, acted upon. The spacecraft's computer systems need to be robust and redundant. You can't have a single computer failure crash the whole mission. So you use multiple independent computers, cross-checking each other, voting on decisions. If one computer gives a different result than the others, it's overruled or flagged for maintenance. But computers fail in space. Radiation causes bit flips, where a cosmic ray hits memory and randomly changes a 0 to a 1 or vice versa. Over time, these errors accumulate, corrupting data and causing malfunctions. Error-correcting memory helps, storing extra information that allows the computer to detect and fix bit flips. But this adds complexity and overhead. Long-term data storage is another concern. Hard drives have moving parts that wear out. Solid-state drives are more reliable but have limited write cycles. Optical media like DVDs degrade over time. Magnetic tape is durable but slow to access. You need a storage strategy that balances reliability, capacity, access speed, and durability. Maybe you use multiple types of storage, with critical data copied to several different media, ensuring that even if one type fails, others preserve the information. The software running these systems needs to be bulletproof. A bug that causes a crash or incorrect behavior could be catastrophic. So the code is written carefully, reviewed extensively, tested thoroughly. Formal verification methods prove mathematically that the software behaves correctly under all possible conditions. But even with these precautions, unexpected interactions can cause problems. The interaction between hardware degradation and software assumptions might lead to failures that were never anticipated during testing. Updates and patches present a dilemma. On Earth, we routinely update software to fix bugs and add features. But on an interstellar spacecraft, updates are risky. What if the update introduces new bugs? What if it fails to install correctly, leaving the system in a broken state? You need to be extremely conservative. Only updating when absolutely necessary, and having robust rollback mechanisms to revert to the previous version if something goes wrong. Consider the medical capabilities required. The crew will experience all the normal health issues humans face, plus space-specific problems. Broken bones, infections, appendicitis, dental problems, heart attacks, strokes. On Earth, you go to a hospital. In space, the hospital is a small medical bay with limited equipment and supplies. The medical officer needs broad training, essentially a general practitioner with surgical skills, dental knowledge, psychiatric expertise, and the ability to handle emergencies. They need diagnostic equipment, imaging systems to see inside the body, laboratory analysis for blood and other samples, monitoring equipment for vital signs. They need surgical tools, medications, supplies for everything from stitches to major surgery. Telemedicine helps, consulting with specialists on Earth via the time-delayed link. Send detailed descriptions of symptoms, images, test results. Wait 4 years for advice. By the time the advice arrives, the patient has either recovered or died. So the medical officer needs to make decisions independently, using Earth's medical knowledge as a reference, but ultimately relying on their own judgment. Certain medical emergencies might be unsolvable in space. A major trauma, a cancer that requires specialized treatment, a disease that needs equipment not available on the ship. In those cases, the patient might die despite the crew's best efforts. This is a grim reality of space exploration, the acceptance that not everyone will survive, that some situations are beyond your ability to handle. Mental health is equally important. The crew will experience stress, anxiety, depression, grief. They'll miss Earth, miss people they left behind, struggle with the isolation and confinement. The medical officer needs to provide psychological support, counseling, possibly medication if needed. But they're also part of the crew, subject to the same stresses. Who supports them? Peer support becomes essential. Crew members looking out for each other, recognizing signs of distress, offering help. Regular check-ins, both formal and informal, to assess everyone's mental state. Activities that build cohesion and morale, celebrations, rituals, shared experiences. The culture of the crew matters as much as the technical systems. Let's examine the arrival phase more deeply. As you approach Proxima Centauri, the character of the mission changes dramatically. For decades, you've been coasting, maintaining systems, conducting experiments, living a routine life. Now you're braking, preparing to enter orbit, getting ready to explore an alien star system. The excitement is palpable, but so is the stress. Deceleration requires the same massive energy expenditure as acceleration. If you accelerated for 1 year to reach 10% light speed, you need to decelerate for approximately 1 year to slow down. During this time, the engines are firing continuously, producing thrust that pins you against the aft bulkhead. You experience weight for the first time in decades, but it's in the wrong direction. Everything is reversed. The floor becomes the ceiling. Equipment secured for microgravity needs to be resecured for thrust gravity. Your trajectory needs to be precise. Too much braking and you end up moving too slowly, taking years to reach Proxima Centauri after your engines shut down. Too little and you fly past at high speed, unable to enter orbit. You're threading a needle, adjusting your thrust constantly based on navigation data, compensating for the gravitational pull of Proxima Centauri and any planets in the system. As the star grows brighter, your instruments begin collecting real data. Spectrographic analysis reveals the star's composition, temperature, activity level. You map the positions and orbits of any planets, moons, asteroids. You search for signs of unusual phenomena, artificial structures, electromagnetic emissions, anything that might indicate technology. Proxima b becomes more than a point of light. You begin to resolve details. If it has an atmosphere. Spectroscopy reveals its composition. Water vapor, oxygen, carbon dioxide, methane, each molecule leaves a distinctive signature in the star's light as it passes through the atmosphere. The presence or absence of certain gases tells you about the planet's geology, chemistry, and potentially biology. Oxygen is particularly interesting. In large quantities, it suggests life, because oxygen is reactive and doesn't persist in atmospheres without constant replenishment. On Earth, plants and photosynthetic bacteria produce oxygen. Without life, Earth's atmosphere would have little free oxygen. Finding oxygen on Proxima b would be compelling evidence for biology, though not conclusive. Geological processes can produce oxygen too, though usually not in large amounts. Methane combined with oxygen is even more interesting. These two gases react with each other, so finding both in an atmosphere suggests active production of at least one, possibly both. On Earth, methane comes from both biological sources like bacteria and geological sources like volcanic activity. Sorting out the origin requires detailed analysis, but the combination is a potential biosignature worth investigating. As you enter orbit, you conduct systematic surveys, imaging the planet's surface at different wavelengths, from ultraviolet through visible to infrared, creating maps of topography, surface composition, temperature distribution, looking for liquid water, vegetation if it exists, signs of seasonal changes or weather patterns. Every piece of data refines your understanding and guides decisions about where to focus detailed study. If you brought landers or probes, this is when you deploy them. Small spacecraft separate from the main ship, descend through the atmosphere if there is one, touch down on the surface. They carry instruments to analyze soil, measure atmospheric pressure and temperature, search for organic molecules, test for biological activity. The Viking landers did this on Mars in the 1970s. Proxima B landers would use similar techniques but adapted for an alien environment whose conditions you're still learning. Communication with the landers is direct since they're nearby, no light-year delays. But commands still need to be thoughtful. If a lander encounters an unexpected situation, it needs autonomy to make decisions without waiting for instructions. Programming that autonomy requires anticipating what might happen, giving the lander decision trees or AI systems that can adapt to surprises. Sample return is the holy grail. Bringing material from Proxima B back to the orbiting ship for detailed analysis. This requires the lander to have ascent capability, to launch from the surface and rendezvous with the main spacecraft. That's complex and expensive in terms of mass and fuel, but the scientific return is enormous. You can conduct analyses impossible with remote instruments, looking at samples under microscopes, running chemical tests, searching for microbes or fossils. But sample return also raises the contamination issue. If there's life on Proxima B, you're bringing it aboard your spacecraft. What if it's dangerous? What if it infects the crew? The risk seems low since alien biochemistry probably isn't compatible with human biology, but we don't know. Science fiction is full of scenarios where alien microbes cause havoc. The sensible approach is strict containment, keeping return samples in isolated environments, studying them remotely until you're confident they're safe. The research you conduct at Proxima Centauri will answer fundamental questions. Is there life beyond Earth? What are the conditions on planets around red dwarf stars? How common are habitable environments in the galaxy? But it will also raise new questions, ones you can't anticipate until you see what's actually there. Good science often leads to more questions than answers, opening new avenues of inquiry. Eventually, the mission ends. You've gathered your data, conducted your experiments, answered what questions you can. Now you face a choice: stay or return. Staying means establishing a permanent presence, using local resources to sustain yourself, making Proxima Centauri your home. Returning means another 40-year journey back to Earth, arriving to a world that's aged 80 years since you left, fundamentally changed in ways you can only guess. Returning requires saving enough fuel for the journey home, which means your spacecraft needs to be even larger at launch to carry that extra fuel. Or you manufacture fuel at Proxima Centauri, mining asteroids or comets for hydrogen and helium, refilling your tanks before departure. This adds years to the mission, time spent building mining infrastructure rather than conducting science, but it makes the round trip feasible. The journey home is a mirror of the journey out. Acceleration, coasting, deceleration. But psychologically it's different. You're heading towards something known rather than unknown. Earth is your destination, home, but it's not the home you left. Everyone you knew is elderly or dead. The culture has drifted. Technology has advanced. You're returning strangers to a strange land. Assuming you survive the return, assuming your spacecraft holds together for 80 years of operation, you re-enter Earth's solar system triumphant. You've done what no humans have done before, traveled to another star and returned. The data you carry, the experiences you've had, the samples if you brought any, these are priceless contributions to human knowledge. But you personally have paid an enormous price. You've spent most of your adult life in a metal tube, missed the entire lives of everyone you cared about, and returned to find yourself obsolete. The skills you trained in are outdated. The world has moved on. You're a living relic, honored for your achievement but disconnected from the society you returned to. This sacrifice is the human cost of interstellar exploration at sublight speeds. Maybe future travelers won't face it if we develop better propulsion or suspended animation. But the first travelers will. They'll be pioneers in the truest sense, venturing into the unknown with full knowledge that they're giving up any normal life in exchange for the chance to explore. Why would anyone do it? The same reason people have always explored. Curiosity, ambition, a desire to push boundaries, to test themselves against the ultimate challenge. The same reason astronauts today volunteer for missions to Mars despite the risks and hardships. Because some people look at impossible challenges and see opportunities. Because the alternative, staying home, staying safe, is unthinkable to them. These are the people who will fly from Earth to Proxima Centauri. Exceptional individuals driven by exceptional motivations, willing to make exceptional sacrifices. We should honor them not just for their achievement, but for their willingness to venture into the darkness so the rest of us can benefit from what they discover. The ultimate legacy of a Proxima Centauri mission isn't the data or the samples or even the establishment of a colony. It's the proof that we can do it. That interstellar travel, while difficult and expensive and risky, is possible. That the stars aren't forever out of reach. Once we've done it once, we can do it again. And again. Each mission building on the lessons of the previous ones, refining the technology, improving the procedures, reducing the risks. The second mission to Proxima Centauri will be easier than the first. The 10th will be routine. Eventually, Proxima Centauri becomes just another destination, not the ultimate challenge but a waypoint on humanity's expansion into the cosmos. And from there, we reach further. 5 light-years to Barnard's star. 8 light-years to Wolf 359. 11 light-years to Sirius. Slowly, methodically, humans spread throughout the local neighborhood of stars. Each new settlement becomes a launching point for further exploration. Ships built at Proxima Centauri don't need to travel all the way from Earth, saving time and energy. Resources extracted from asteroids and planets reduce the need to transport materials from Earth. Technology developed in one colony spreads to others, accelerating progress across multiple star systems. Over centuries, this creates a network of human settlements, each independent but connected by the thin threads of light-speed communication. A vast community spanning dozens or hundreds of light years, united by common origin but diverse in experience and culture. This is the long-term vision, the endgame of interstellar exploration. And it all starts with a single journey. One spacecraft. One crew. Flying from Earth to Proxima Centauri. That's how it begins. That's how we take our first steps into the galaxy. That's how we transform from a single planet species into something greater, something that belongs not just to Earth but to the cosmos itself.